Okay, so last time I just repeated a little of 1-bit and 2-bit predictors. Talked also about compilers, doing prediction of branches based on previous executions of the program, where they profile the program, and using that information, the compiler can generate whether a branch will be taken or not instruction. So based, it helps that, but it's not very useful. So they started doing, these are the dynamic branch prediction techniques that we are discussing now. And so the two-bit predictor, this is the state diagram, like I said, which the Georgia Tech people use. The textbook uses a different state diagram. I was thinking about it. I feel that we can use either of the two state diagrams. So in one case, the state change from 00 to 11 will happen if there are 3 taken branches, like in this FSM. In the other FSM, it will happen in 2 taken branches. Okay, so either of the 2 FSMs you can look at and analyze. That will, we analyzed in the last class, if we have patterns of this sort, what happens, and found that for typical loops, 0, 1 or 1, 0 is a good starting point, but it can lead to the worst case that every prediction is mispredicted, wrong, for alternating taken, not taken, uh, you know, patterns. So the question after looking at some branch prediction techniques is, why are we so worried about branch prediction? Like, in this case, if you have 0, 1, or in fact, if you have a TTTT and D 1, 0, then you'll have one misprediction exactly at the end when you are actually having a prediction of taken and you are doing a not taken. So if you compare it to the 1-bit predictor, you have 2 mispredictions per loop, whereas here you will have 1 misprediction in the loop. And there will be some patterns where even the 2-bit predictor doesn't work so well. And why is branch prediction becoming so important? So the branch prediction has become important because most of the processors today do not issue one instruction in every clock cycle. They actually issue multiple instructions in a single clock cycle. So if you don't predict a branch, or you have a mispredicted branch, the situation is going to be very bad. Like I wrote in the example, supposing we say a processor issues 5 instructions in each clock cycle, and the branch delay is 3 clock cycles. So that is basically, when we say branch delay, it means that, the time at which the branch was issued and the time at which you know both whether the branch will be taken or not, and the target address. Okay, the difference between the two. Now, in all those clock cycles, the issue of the next sequential instruction will be happening if there is no branch prediction. If there is a branch prediction and it is a misprediction, then it will be bringing in instructions from the wrong location again. So if we say that our branch prediction is not taken, then in that case also we'll be getting instructions from the next sequential instruction. So all such instructions which we fetch will be wasted. Now in every clock cycle, we are fetching 5 instructions. So if you have a branch delay of 3 cycles, then you have 15 instructions which have been fetched and they have moved into the decode stage, and so on. So a lot of work is wasted, and we have to convert all of them into no ops, and then again start fetching instructions from the right location. So this is really, very, very bad situation for the processors. So branch prediction became very, very important with these processors, which are called superscalars, where you have multiple issues of instructions per clock cycle. Okay. So the next predictor that we will be looking at is what is called as a correlating or global predictor. So what is this thing? If we look at the code, which is given below, this is directly an example from the textbook itself. If AA equal to 2, then assign AA to 0, and if BB equal to 2, BB is assigned to 0. And then you have another branch, which if AA not equal to BB. Okay. Now in the outcome, in the above code, branch B3 is taken or not taken is dependent on the taken or not taken of branch 1 and 2, right? If both branch 1 and 2 are taken, then, if both the branches are not taken, then, B3 will be taken. Okay. So basically, what we are saying is there are certain branches whose behavior is dependent on the outcome of some branches which occurred before this branch actually in the code. So it's not dependent entirely on its own behavior. Like if you take a regular loop, then, you will say for I equal to 0 to 10, the outcome of that loop in one iteration is mostly dependent on the outcome in the previous, iteration, and it's not dependent on any other branch. Okay, so those are where local predictors will work very well. But a branch of this sort whose outcome is dependent on the outcome of the previous branches, we need to maintain history of all the branches until now, or some branches until now. Okay. And based on the history of the outcome of the previous branches, we will decide or predict whether this branch will be taken or not. So we are essentially maintaining not a local history, because when we say branch history table, whether it's a single bit predictor or a 2-bit predictor, we are saying was the branch taken last time or not taken? In the case of single bit predictor, if it was taken, we predict it's taken again. If it's a 2-bit predictor, depending on whether it's a 0, 1, 1, 0, 0, 0, 1, 1, and we decide, we predict whether it will be taken or not. So there we are maintaining the last 2 outcomes of the loop. Here we need to maintain similarly the history of the previous branches, and then we use the behavior of the previous branches to predict the outcome of this branch. So this is what is called as a correlating predictor or global predictor. Okay. And then the generalization for this is MN predictor. Okay. In general, we maintain the history of the last M branches, okay, in an M-bit shift register. I think some of you or all of you are familiar with the shift register. Basically, we shift it to the left, okay, or to the right, whichever way we want to look at it. If we take the, leftmost bit to be the latest branch, then we shift right and we set the bit of the leftmost bit to be either 0 or 1, depending on whether the latest branch was taken or not taken. So every time we come to a branch instruction, we do a shift of this, register value and set the new bit depending on the outcome of the current branch that we are looking at. So that is the M-bit shift register, which is used to maintain the global history of M branches. Okay. And then you can use the value in this mbit register with some bits of the branch address to index into a table, and the table will give you the prediction for this branch, whether it'll be taken or not. Each entry of this table will be having n bits, so you can have a 2-bit predictor there if you want. So then you have mn will be basically m2 predictor, okay? And so an example here, a 2-2 correlating or global predictor, supposing you say that the branch address is 12 bits, a 12-bit branch address. So there's a 12-bit processor that we are talking about. Then you have a two previous branches history is maintained. So you have a 2-bit shift register, which is a 2-bit global branch history. Then you take 4 bits from the branch address, concatenate those 4 bits with the branch global history, and use that to index 64 entries, because you have now 6 bits. You can index into 64 entries, and each entry will be a 2-bit predictor whether it will be taken or not taken. Okay, so this is how the correlating predictor works. Any questions on that?
Ma'am, can you show that code? The last slide. Can you show the last slide once?
This one?
No, the one before. The one with the example code.
Yeah, I have put.
Ma'am, like, won't the compiler be able to convert this to a code that is totally independent of anything else? Like,
no, the thing is the values of AAA and BB won't be known, right?
okay.
If AA and BB were sort of constant, then the compiler can actually easily convert this into, it doesn't even have to evaluate them at runtime. It will evaluate at compile time, and as you say rightly, it will replace it completely with probably very trivial instruction.
Okay.
But when the values are unknown at runtime, I mean, you'll only know at runtime, the compiler doesn't know what to do. So, but the profiling will help. If the values are typically taken, these are the values that are typically given to AA and BB, and they are by most of the inputs that come in, they'll be taken, not taken. This sort of profiling can be done. We can run it with the test suite and profile the program. Based on that, the compiler can actually do a good prediction and rewrite the code, sequencing of the code, right?
Yeah.
Just as in the delayed branch, the compiler decides, okay, I'll put this instruction instead of there, I'll put it here, so that, after the branch, this instruction will be executed, and it will not need to be converted into a no-op. So it's doing some different scheduling, right? It's not actually scheduling the code in exactly the order that we write the program. Similarly, here it can reschedule the code in such a way that it can arrange the code to have the next sequential instruction be the commonly executed instruction based on the branch outcome.
Okay.
So if the common outcome is not taken, okay, no issue, because the very next sequential instruction is taken, so the regular order of the instructions will be preserved. But if the branch is taken, then the target address, whatever instruction is at the target address, will be scheduled as the next sequential instruction by the compiler. So then, you can still proceed with fetching the next instruction, and you will actually be fetching the instruction which will be executed if the branch is taken. So,
Okay.
so they do a lot of such tricks in the compiler. We'll see more tricks once we finish the branch optimizations. So I hope this diagram makes it clear what the correlating or global predictor is doing, right? You have a global history which is concatenated with a branch address, part of the branch address, or the whole branch address, depending. But because nowadays we have 64-bit addresses, nobody will use all of the branch address. They'll take only some bits. They'll normally have about 1K or at the most 4K entries in the predictors. So that's about 12 bits from the branch address that they'll be using. They can concatenate it or in fact XOR also. So how these 6 bits, in our example, we have 64 entries in the predictor table, right? So we need 6 bits to index into those 64 entries. How these 6 bits are generated is not fixed. You can concatenate the values like I showed here. Another way of doing it would be, if you supposing, let us say you are maintaining a 6-bit global history, okay? So if you are maintaining a 6-bit global history, and one of the things they do is they XOR those 6 bits with 6 bits from the branch address and then use that as the index into the table. Okay. The reason I believe they do XOR is that it sort of, otherwise what happens, whatever branch you may be taking, right? If there are 6 bits in the global history, whatever branch you may be taking, the 6 bits remain the same and you will index into the same entry using those 6 bits. But by XORing with the branch address, you are sort of, using information from the branch address also. That makes it much more accurate for that branch, the prediction that you're doing, because now different branches will have different addresses, and when you XOR with the same global history information, the resultant 6 bits will be different for different branches. So you will be able to have a more accurate prediction for each branch. That's what they do. But here, because we are maintaining only a 2-bit global history and we have 64 entries in the predictor table, we are able, we are concatenating the branch address bits to the global history to index into the table. Okay, so, they basically evaluate the, effectiveness of a predictor based on how many bits it is using and how accurate its prediction is, right? I mean, like, you're using more bits you use. Okay, we talked only about 1-bit predictor and 2-bit predictor, but you can also use a 3-bit predictor. I believe that beyond 3-bit predictor, normally the accuracy improvement is not very high. So most processors don't use beyond 3 bits for the predictor value. Okay, so there they go from 000 to 111, and but how many entries do you have in the predictor table? That is one question we need to ask. So your book actually gives you graphs of using, I think 1K, 4K entries and infinite entries, and shows that, the difference in the prediction accuracy is not much when you move from 4K to infinite. So it doesn't matter if you have infinite entries in the table. That's not really necessary for good accuracy or of prediction. For about 4K entries will be sufficient, but you need to do it, in a more clever manner. So they calculate. I mean, again, this calculation is from the book. Example is from the book. Okay, standard 2-bit predictor. MN predictor is a good generalization. Please go back to your programming course. We talk about generalization. So MN predictor is a generalization. So 0-2 correlating predictor is our 2-bit predictor. When we say 0, M, which means that we are maintaining no global history, and we are having 2 bits in the predictor table. So that is exactly what our 2-bit predictor is, right? So MN predictor is a very nice generalization. And now if we have a standard 2-bit predictor with 4K entries, right? We need 12 bits of the branch address to index into these 4K table, right? How many overall bits are you using for this predictor? We have 2 bits per entry and 4K entry, so 8K bits are being used in this predictor. Now, if we are, instead of using a regular 2-bit predictor, we want to use a 2-2 predictor, but whose overall number of bits will be 8K only, right? Then how many entries do we need in the table of that predictor is what this calculation is about. Because when you are comparing one predictor with another predictor, we should compare them such that they have the same number of bits. And then we see what's the accuracy. Okay. Otherwise, it's unfair comparison. One has 16K bits, another has 8K bits. It's not a fair comparison, because the more number of entries or more number of bits you are allowed, the better your accuracy will be. So if we are saying that I want to compare a regular 2-bit predictor with the 2-2 predictor, then we need to have same number of bits in both the predictors. So this is basically the calculation we have. We have 2 bits per entry, n entries, okay, 2n. And then you have two squared possibilities for the global history, right? Because there are 2 bits in the global history, there are 2 squared possibilities on the values there. That all of these bits combinations equal to 8K bits. So the number of entries in the 2-2 predictor will be 1K. Okay. Now, therefore, what you do, you take a typical 2-bit predictor with 4K entries and a 2-2 predictor with 1K entries, and compare what is the accuracy of prediction of these 2 predictors. Okay. That is how you need to compare the accuracy of the predictors. Right? Any questions on that? Mm-hmm. So now we come to the tournament predictors. Okay, so the idea here is that, like I said in the previous discussion, when we talk about loops, they are dependent only about, their outcome is dependent entirely on their previous iteration, right? They are not dependent on some other branch outcome. So there are some branches where the local predictor makes sense. There are some branches where the global predictor makes sense. And a tournament predictor is basically trying to figure out, should we use a local predictor or a global predictor for a particular branch? Okay, so it has information and is able to say, you use the local predictor for this branch. Or it will say, no, this branch is dependent on the outcome of the previous branches, so use the global predictor. the tournament's predictor's business job is that to allow you to determine whether to use a local or global predictor. Okay, so alpha 21264 is the processor that example that the book takes, and it uses an overall size of 29K bits in the predictor. Now, I'll send there is a problem in the 5th edition for the alpha 21264 description. They missed out, I think, at least one paragraph in the 5th edition. I'll send the actual description of the alpha 21264 processor tournament predictor to Bansi to share with all of you, because if you actually calculate or try to calculate the number of bits used by the processor as per the 5th edition, you will never get to the value of 29K. I remember last time when I taught struggling very, very badly, and finally, by sheer accident of some slides I was consulting, I came to know what was the problem, and I had the 4th edition also with me. So I was able to consult the 4th edition and discover that a paragraph went missing in the 5th edition. This time, because I forgot, again I was struggling to calculate and figure out how it's coming to 29K, and finally I remembered that there is a problem in the book. Okay, so this is the alpha predictor. Are you able to see this? I'm sorry, I had to reduce the size because it's not fitting into the slide.
It's visible, ma'am.
Okay, I'm trying to increase it so that it's not so bad. Okay, so as you can see, it's a very complex predictor. Okay, but this is how most of the predictors today are in Intel processors and all. So this was probably the precursor to everything. You should all know that Tex Alpha was a 64-bit 64-bit processor in 93. I think they did it, because I remember in 94 hearing about it. And then, of course, by 96 maximum, 95, 96 time frame, SGI and Sun had 64-bit processors. I don't remember, I have no clue when Intel came up with a 64-bit processor because it was so late. Similarly, Sun had a very, I think by 2006, I think they had this processor which had 64 cores. I remember. At that time, Intel had just come out with a dual processor, not even a dual core. Okay, they were far ahead of all these things, and so it's interesting to see their stuff. All right, I think we are running out of time, so we'll do the usual thing of exiting now. When I exit in the middle of discussion about the predictor, and rejoin, okay, so that we can do it in one shot.